All right, hi everybody, and welcome to Saturn. Saturn is, I'm a little excited because Saturn is my favorite planet. So I'm a little pumped up here. Let's hit the vital stats here for the sixth planet, which is Saturn. So the semi-major axis is about 9.5 AU. So that's a big jump between Jupiter, which was at like 5.2, and 9.5. It's almost twice the distance to the Sun as it is for Jupiter. So there's a lot of planets inside the first 5 AU, and then there's a huge gap until the next one, which is Saturn. Okay, so it's really quite a jump out, and this is typical of the outer planets, these big gaps between them. Let's see, the orbital period is 29.4 Earth years. That's almost 30 years to go around the sky once. I first started watching the sky when I was about 19 or 20 years old, and so Saturn has had enough time to go around about once. I'm right just a little bit past 50 right now, so it has, in my life, and since I've been about a year or two ago, Saturn returned to the same place in the sky where I first saw it. I've been watching it for 30 years. So that's a pretty long period of time. And for a long time, that was the longest known natural unit of time. You know, the seasons repeat, right, every year. The days repeat every day, you know. And then you have the annual seasons. You have Jupiter, which is orbiting every 12 years, but Saturn took 30 years, and for thousands of years, that was the longest natural known period of time, 30 years. Rotation period, it rotates pretty quickly, just like all the outer planets do. Let's see, Saturn is there about 0.44 Earth days, which is about, I think, 17 hours. No, I'm sorry, 10. That's the next planet. About 10 and a half hours for one rotation. Jupiter goes a little bit faster, but Saturn takes about 10 and a half hours to rotate once. And that's an average. It turns out that the big gas planets don't rotate at the same rate everywhere. They rotate more quickly at the equator than they do at the poles. It's called differential rotation. We'll see it again when we get to the Sun. Anything that's made of gas, like the Sun or one of these planets like Jupiter or Saturn, rotates more quickly at the equator than at the poles. Again, it's called differential rotation. This is at the equator. This is the fastest value, the smallest period. Let's see, the mass of Saturn comes in at 95 Earth masses. Compare that to 318 for Jupiter, so it's quite a bit lighter than Jupiter is, but still almost 100 times the mass of the Sun. The radius of Saturn is about 9.5. That's not right. Yes, it is 9.5 Earth radii. Compare that to 12 for Jupiter, or 11 for Jupiter. The number of moons. Here we go. Boom. 82. As of the beginning of this class. I haven't checked since the class started a few weeks ago, but 82 moons. The density, this is the interesting, amusing number. We'll come back to it. 690 kilograms per meter cubed. Okay, we'll come back to that. The obliquity, that is the eccentricity of the orbit, is a little bit high. Okay, higher than the Earth's, less than Mars's, less than Mercury's. Let's see, magnetic field is approximately equal to that of the Earth at the cloud tops. Okay, I'm talking about the magnetic field, sort of, there's only no surface of Saturn, like there's no surface of Jupiter, but these magnetic fields are measured at the surface, at the outermost parts of the planet, so the part that we can see. Pardon me. Oh, I got my number wrong. That 0.056 is not the obliquity or the axial tilt, that's the eccentricity. So my comments about that being less than Mars, less than Mercury, but more than Earth's have to do with the obliquity. Okay. Have to do with the eccentricity, rather. Obliquity of Saturn is pretty high. It's about 26, make sure I got this right, yeah, 26.7 degrees. So it too has seasons. Okay, it has seasons, unlike, say, Venus. And finally, the surface temperature is quite cold, 134 kelvins, which is negative 219 degrees Fahrenheit. It is cold out there, y'all. Cold. Okay. And again, surface temperature. There's really no surface, like I've said. It's a big ball of gas. You can't go stand on it. So this is the temperature sort of at the cloud tops there. Okay. So that's that. Those are the vital stats. What else do I want to say about Saturn here before we go on much further? Oh, I want to come back to this number. Yeah. This, mark it in pink here. This density. This is way lower than any other planet. It's like about half that of the next density. So it's a very small number. Remember, the inner planets are in the like 4,000 to 5,000 range. Jupiter came in at 1,300. And remember what this number is. It's the density. Here's my meter stick, our handy meter stick. If we went, sort of took an average chunk of Earth, this big, a box of the average chunk of Earth, this big on a side, this deep, this high, okay, a cube this big, this width, this depth, this height, a big cube. On Earth, that would have a mass of about 5,400 kilograms or about 10,000 pounds. Okay, something like that. On Jupiter, it'd be far less, but instead of 5,400 kilograms, it would have a mass of only 690 kilograms. Now, this is less dense than water. Water is 1,000 kilograms per meter cubed. So Saturn is less dense than water, which means if you could build a big enough bathtub, Saturn would float in it with plenty of it left over, sticking out of the top. If you could put Saturn into a bathtub, you know, it would float with something like that. Of course, the rings would sink, but it would float, okay, on water if we could find a bathtub big enough, which we, of course, cannot. A couple other things to say about it that are of some interest. Let me actually pull this out of my notebook here so I'll stop looking down away from the camera. Pardon me just one second. Be patient. Patience. Let's see, where is it? Oh, it's over here. Sorry for that. The composition of Saturn is similar to Jupiter, but not really the same. It's about 92.4% hydrogen, only about 7.4% helium, CH4, which is methane. We'll be seeing methane again quite a lot in the outer solar system. It's about 0.2%, and I want you to watch that number. And finally, NH3, which is ammonia, has about 0.02%. So that's very different from the inner solar system. Similar to Jupiter in that it's mostly hydrogen, some helium, and other junk. Okay, but there's far less helium in Saturn's clouds than there is in Jupiter's clouds. You read your textbook, you'll see that's because that you know how there's rain on the Earth where you have liquid water falling? There's rain on Saturn and it's liquid helium. It's pretty much near constant. Well, several layers down under the cloud tops. So that removes helium from the upper decks of the atmosphere, which is what we're looking at which is what we're referring to when we talk about the composition. So the helium is in there, it's just more concentrated deeper down where we can't see it. It's raining out there. The conditions, the pressure and temperature there on the upper cloud decks of Saturn are such that helium will condense and fall like rain. So it's depleted somewhat in the upper atmosphere where we are looking when we make these measurements. Okay. Last thing I want to mention is something called ring crossings. In this video, we have 2 more videos about my favorite planet. Ring crossings. All right, when Galileo first looked at Saturn through his telescope, he looked at all the planets that he could see with his eye, through the telescope. He thought it looked something like this. He thought it looked like a single large planet with 2 little planets to either side, and that was in about 1610. Now, of course, that's not what it was. What he was looking at was the rings, but it was his telescope was quite crude, and that's the best that he could see. Very quickly after that, his telescope got better, and he thought it looked something like that, which is closer. But in 1612, he looked again, and all he saw was that. What had happened was this. When we look at Saturn during Saturn's summer, or let's say winter, this is Saturn's winter, not ours. We see, so back 2002, for example, was Saturn's last winter. Okay? We're talking about northern hemisphere winter on Saturn. What we see when we look at Saturn, when Saturn's in winter, is this. The rings look like that. But later on in 2009, when we're at in winter, in the spring, again, this is Saturn winter and spring, not our spring. Saturn's winter and spring. What has happened by this point is that we are now looking at the rings edge on like that, and they're so thin that from the point of view of the Earth, they disappear. Poof! We can't see them. You have to have a super, super, super good telescope to see them. Okay? So in 2009, if you try to look at Saturn through the telescope, you would not see the rings at all. But if you waited a little while until Saturn's northern summer, which was a couple years ago in 2017, that'd be 3 years ago. Now we're seeing the rings again. Looks like that. Notice the rings are now crossing at the bottom, not the top. Okay, from Earth's point of view. Then we have to wait another several years. So in Saturn's fall, which will be 2024, just a few years from now, we will again be looking at the rings edge on. The rings are very thin, maybe only, between 5 and 10 miles thick. They're hundreds of thousands of miles across, side to side, But they're super thin. So when they're edge on, we can't see them at all. Okay, I draw the line here and here, but in a telescope, you just can't see them. You have to have like Hubble to be able to see them well. Okay, when they're truly on edge on. Okay, and this is because of this tilt right here, that 26.7 degree tilt. If we're not tilted that way, then we would always be able to see the rings. Okay, so over time lapse, the rings kind of do this sort of thing. So sometimes they're edge on, sometimes they're face on, sometimes they're edge on, sometimes they're face on. Okay. Sort of a little wobble. I don't really have anything I can demonstrate it with here, but I hope you get the point. Sort of like a little top processing around like this. That's sort of what the rings do over time. So there are ring crossings. And so what happened with, this was Galileo, remember? What happened with Galileo is when he first saw it in 1610, and shortly after, so these are both 1610 here, he was looking at the rings either it was either winter or summer on Saturn. But by 1612, it had become either spring or fall. I can't remember which one it was. But he was looking at the rings edge on, and so he couldn't even see them. His telescope was not nearly good enough to actually see the rings when they're edge on. All right, so those are Saturn's ring crossing. So right now, we're between 2017 and 2024. We got a pretty good view of the rings right now. But over the next 4 years, they're going to get harder and harder to see, and then by 2024, they're going to essentially disappear in a small telescope as seen from Earth. Speaking of the rings, they're up next.